Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is Previously we pointed out that undetermined coefficients has two inherent weaknesses that limit its wider applicability. The differential equation must have constant coefficients, and the input function g of x must be of a type listed that we know how to annihilate it. In this section, we examine a method for determining a particular solution y sub p of a non-homogeneous linear differential equation that has, in theory, no such restrictions on it. You might not be able to do the integrals, but no such restriction is imposed. This method is due to the great mathematician Lagrange, and it's called variation of parameters. There is some motivational material, but I'm not going to talk about that. We're going to cut to the chase. Okay, so what we're going to do is we're going to start with a second order linear differential equation that looks like this, and notice I'm letting it have variable coefficients, and then I'm going to divide all the way through by a2 of x as I normally do, and I change it into this. Now if these were constants, and they're not necessarily constants here, what this would mean is that this would be easy to solve the homogeneous equation and find y1 and y2 that were solutions to that, and then we have ways if f of x is nice enough. But we're not going to pretend that f of x is nice enough. But the idea that Lagrange had was, gee, instead of saying the complementary solution is c1 times y of x plus c2 times y2 of x, what if we let them be variable? These c1 and c2 are parameters. Let them be variable, and we'll let them be u1 of x and u2 of x. So we found two solutions to the homogeneous equation, and what we're able to do then is we're able to create this y, and we'll plug it in and see what happens. So we're going to take this y that has known y1 and y2, but we don't know what u1 and u2 are yet. We're going to take this and we'll plug this into our equation 6 and do some calculations. Now you do have to do quite a bit of calculation to do this. So when you plug it in, this is what you'll get for your first derivative, and this is what you'll get for the second derivative. A lot of product rule. You should really check and make sure you understand where this is coming from. But now what I'm going to do is I'm going to reorganize that. So I'm looking at this, and I realize that if I reorganize it, I can factor u1 out of here, and I have something that's 0 because this is a solution to the homogeneous equation. And u2 likewise is a solution to the homogeneous equation. So those two terms drop out. Moreover, I can observe that there are some nice things going on with derivatives of products. And so we get expressions that look like this. Again, you should check and make sure you understand where all this is coming from. And I can even reorganize these because this derivative and this derivative is just the derivative of the sum, and so on and so forth. So you see we have this expression. But then Lagrange said, well, gee, I would really like to find out what u1 and u2 are, but I need two equations to find out what two unknowns are. So maybe I can force some things to happen. So he said, what happens if I insist that y1 u1 prime plus y2 u2 prime is 0? That means insist that this is 0. And moreover, what if he insists that this one is 0 as well, which means that this one will be equal to 0? Well, if you put all those zeros in, this is what you have. You now have two equations and two unknowns. u1 prime is an unknown, u2 prime is an unknown. Those are derivatives. u1 prime is an unknown and u2 prime is an unknown. And you have two equations and two unknowns. Well, we know how to solve such equations. And in fact, we can use Cramer's rule that you studied in your pre-calculus, and I think this is discussed in an appendix as well. But we can say, all right, how would we solve these using Cramer's rule? And so what we'll end up with is u1 prime is equal to w1 over w, and W is shown here as this determinant. W2 or W1 is shown there here, and W2 is shown here. And again, this lines up with Cramer's rule. So U1 prime is W1 over W, and U2 prime is W2 over W. Now you see, and by the way, this is the step that I go directly to, because now what I can do is I can solve this differential equation for U1 and U2. I don't have to worry about my constants of integration, and I will have a solution to the problem. They're found by integrating the results. And by the way, you notice that this W actually is the Wronskian, and you know the Wronskian doesn't equal to 0, so it's okay to divide by it. Okay, I told you where I went to, and I usually go to this point and I say U1 prime is going to be this, U2 prime is going to be this, but it is important that you remember which one is 1 and which one is 2. That's something that some students don't do carefully, and that gets them into trouble. And then the particular solution is this one, and the general solution is the complementary solution plus the particular solution. So this is your go-to step, and then you solve it from there. Now, some people like formulas. I don't so much, but here is formulas that can be used as well to get those solutions. And you see it is a linear combination of y1 and y2, and you do these calculations of those integrals. Pretty powerful stuff. So here's a problem for you to do. Find a general solution to this differential equation. Realize that you cannot do this by annihilators because you don't know how to annihilate the tangent. You know what to do. And I will see you in 19.